The room you're sitting in right now is not empty. Not even close. Every cubic centimeter of empty space around you is a boiling, churning storm of invisible energy and particles that blink in and out of existence billions of times per second, and physicists have the measurements to prove it. Fact number 1, empty space has a measurable energy, and it's enormous. In quantum field theory, the lowest possible energy state of any system is not zero. It's called the zero-point energy, and it exists because of Heisenberg's uncertainty principle, the fundamental rule of quantum mechanics that says you can never simultaneously know both the exact position and exact momentum of a particle. This means fields, think of them as invisible fabric stretching across all of space, can never fully settle down to zero activity. They always jitter. They always fluctuate. And those fluctuations carry real, measurable energy. Here's where it gets staggering. When physicists first tried to calculate exactly how much zero-point energy should exist in a vacuum, using quantum field theory, they got a number. Then they compared it to what astronomers actually observe in the universe. The theoretical prediction was off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This is widely described as the single worst prediction in the history of science, not because physics is wrong, but because something deep and unknown is going on in the quantum vacuum that we still don't fully understand. That mystery alone keeps thousands of physicists employed worldwide. Visual note: show an infographic comparing the theoretical vacuum energy value versus observed cosmological constant on a logarithmic scale bar chart. Use contrasting colors, no imagery. Fact number 2, particles literally appear from nothing, then vanish. Inside the quantum vacuum, pairs of particles spontaneously pop into existence from pure energy fluctuations. We call them virtual particles. An electron and its antiparticle, a positron, for example, can materialize together from nothingness, exist for a vanishingly small fraction of a second, then annihilate each other and disappear back into the vacuum. This sounds like pure fantasy, but it is a cornerstone of quantum electrodynamics, or QED, the most precisely tested theory in the history of science. How precise? QED predicted the magnetic moment of the electron, a property describing how it behaves like a tiny magnet, to be 1.00115965218128. Experimental measurements confirmed 1.00115965218059. That's an agreement to within 10 parts per trillion. No other scientific theory in human history has been confirmed to that level of accuracy. And virtual particles are baked into the math. They are not optional. They have to be there. Visual note: animated diagram showing particle-antiparticle pair creation and annihilation loop with labeled arrows, academic style, clean infographic. Fact number 3, the vacuum can push two metal plates together with no force applied. In 1948, Dutch physicist Hendrik Casimir made a startling prediction. If you take two perfectly flat, uncharged metal plates and place them just nanometers apart in a true vacuum, the quantum vacuum itself will push them together. No magnets. No charge. No glue. Just empty space generating immeasurable force. The reason is elegant. Between the plates, only certain wavelengths of virtual photons, light particles, can fit. It's like trying to play certain musical notes inside a small box, you simply can't fit the long ones. But outside the plates, all wavelengths of virtual photons exist. That imbalance creates a pressure differential, more quantum activity outside than between, and the plates get pushed inward. This effect, the Casimir effect, was experimentally confirmed to within 5% accuracy by physicist Steve Lamoro at the University of Washington in 1997. The first direct physical proof that quantum vacuum fluctuations exert real, measurable mechanical force in the macroscopic world. The force is tiny, equivalent to about 1/10,000th of the weight of a mosquito when plates are separated by 1 micrometer, but it is real, reproducible, and now being studied for applications in nanoscale engineering and microelectronics. Visual note: side-by-side diagram of virtual photon wavelengths inside versus outside the plates, show pressure arrows pointing inward. Clean academic style. Fact number 4, a black hole's death is powered by the quantum vacuum. In 1974, Stephen Hawking combined quantum mechanics with general relativity and derived one of the most surprising results in all of physics. Black holes, objects so dense that not even light can escape, are slowly evaporating because of the quantum vacuum. Here's the mechanism. Virtual particle pairs appear constantly near the event horizon, the boundary of a black hole. Normally they annihilate almost instantly. But right at the edge of the event horizon, one particle can fall in while the other escapes into space. The escaping particle becomes real, it carries real energy away, and the black hole must pay the energy debt. It loses mass. Over an unimaginably long time, the black hole shrinks and eventually evaporates entirely. This radiation, called Hawking radiation, has not yet been directly detected from an astrophysical black hole because the effect is incredibly faint for large black holes. A black hole with the mass of our Sun would have a Hawking temperature of just 60 billionths of a Kelvin, essentially indistinguishable from the cosmic microwave background. But in 2019, researchers at the Technion, Israel Institute of Technology, created an analog black hole using ultra-cold rubidium atoms and detected the analog of Hawking radiation experimentally for the first time, publishing in Nature. The quantum vacuum is literally responsible for the eventual death of every black hole in the universe. Visual note, infographic diagram of event horizon with labeled particle pair separation, one arrow inward, one outward. No real imagery. Fact number 5. The quantum vacuum may be causing the universe to accelerate apart. In 1998, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, discovered something that won the 2011 Nobel Prize in Physics. The expansion of the universe is not slowing down due to gravity as expected. It is speeding up. Something is pushing everything apart, and that something is called dark energy. The leading candidate for dark energy is the energy of the quantum vacuum itself, the cosmological constant, which Einstein originally introduced in 1917 and famously called his greatest blunder before removing it, only for it to come roaring back in 1998. Current measurements from the Planck satellite confirm that dark energy makes up approximately 68.3% of the total energy content of the observable universe. The quantum vacuum, that seething sea of nothingness, may literally be the dominant ingredient of all that exists. Every galaxy you've ever seen in a photograph is being pushed away from every other galaxy right now because empty space refuses to be truly empty. Visual note, pie chart showing universe composition, 68.3% dark energy, 26.8% dark matter, 4.9% ordinary matter, in contrasting color blocks. Fact number 6. The vacuum has already triggered at least one universe-scale phase transition, and may trigger another. This is the one that keeps physicists up at night. The quantum vacuum may not be in its lowest possible energy state. It might be in a metastable state, what physicists call a false vacuum. Think of it like a ball sitting in a small valley on the side of a mountain. It appears stable. But if it gets nudged, it will roll down to the true, deeper valley, the true vacuum, releasing an incomprehensible amount of energy. If the Higgs field, which gives particles their mass, is currently in a false vacuum, then at some random point anywhere in the universe, a quantum fluctuation could trigger a bubble of true vacuum to nucleate. That bubble would expand outward at the speed of light, and inside it, the laws of physics as we know them would be completely different. The masses of all particles would change. Atoms as we know them could not exist. Life would be impossible. In 2012, the Large Hadron Collider at CERN measured the Higgs boson mass at approximately 125.25 GeV. Physicists then ran the calculation. That specific mass puts the Higgs field precisely in, or extremely close to, the metastable boundary zone. A 2018 paper in Physical Review D confirmed this, noting the universe appears to be in a metastable state. The good news? If such a bubble formed tomorrow, we would never see it coming. It travels at light speed. We'd simply cease to exist between one Planck instant and the next. The quantum vacuum may have already decided the universe's fate. Visual note, energy landscape diagram with labeled false vacuum and true vacuum valleys, bubble nucleation arrow, clean physics infographic style. Fact number 7. The quantum vacuum measurably shifts the energy levels of hydrogen atoms, observed in 1947. Before Casimir, before Hawking, the first concrete experimental fingerprint of quantum vacuum fluctuations was measured by physicist Willis Lamb in 1947, a discovery so significant it won him the Nobel Prize in Physics in 1955. Using microwave techniques developed during World War II, Lamb measured the energy levels of hydrogen atoms with unprecedented precision. Classical physics and even early quantum mechanics predicted that two specific energy levels in hydrogen, called the 2s1/2 and 2p1/2 states, should be identical. But Lamb found they were not. There was a tiny but unmistakable shift between them, now called the Lamb shift, measuring approximately 1057.845 MHz. That tiny gap only exists because virtual photons from the quantum vacuum constantly buffet the electron in the hydrogen atom, slightly nudging its energy levels. Remove the quantum vacuum from your equations and you cannot explain the Lamb shift. It's there. It's real. It's measured to extraordinary precision. And it proves that even the electrons in the atoms of your own body are being continuously jostled by the quantum foam of empty space. Visual note, energy level diagram for hydrogen showing 2s1/2 and 2p1/2 split with Lamb shift labeled in megahertz, academic style, color-coded. Fact number 8. Scientists have extracted usable energy from the quantum vacuum, and it's called the dynamical Casimir effect. Everything we've discussed so far might sound purely theoretical, but in 2011, a team at Chalmers University of Technology in Sweden published a landmark paper in the journal Nature. They had successfully extracted real photons from the quantum vacuum for the first time in a laboratory. This is called the dynamical Casimir effect. Here's how they did it. Rather than physically moving metal plates, which would be nearly impossible at the speeds required, the team used a superconducting quantum interference device, a SQUID, connected to a microwave transmission line. By rapidly modulating the electrical length of the line using magnetic fields, they effectively created a mirror that was moving at approximately 25% of the speed of light. When a mirror moves fast enough through the quantum vacuum, it can transfer enough energy to virtual photons to convert them into real, detectable photons. The team detected a measurable flux of real microwave photons, created from nothing but the motion of a quantum mirror through empty space. This is not science fiction. This is published, peer-reviewed, experimentally replicated physics. The quantum vacuum is not a passive backdrop to the universe. It is an active, energetic, structured medium that physicists are only beginning to learn how to interact with. The idea of one day harvesting that energy at scale remains highly speculative and faces enormous theoretical obstacles, but the proof of concept exists. Empty space gave us light. Visual note, schematic diagram of SQUID circuit with microwave transmission line, virtual photon conversion arrow, labeled output, clean academic diagram. So the next time someone tells you that a room is empty, or that space is just nothingness between stars, you can tell them the truth, it's a quantum storm. It's the engine driving the universe apart, the mechanism erasing black holes, the jitter that shapes every atom in your body, and possibly the ticking clock on the lifespan of all physical reality. The most important thing in the universe might just be nothing. Subscribe to Moonlit Minds for daily mind-blowing facts that will change how you see the world.